Hello, everyone, and welcome to the Surface Ventures webinar on hydrogen tribology. It's great to see quite a few people are saying hello in the chat already. That's fantastic. It'd be great if you could just tell us where you're joining from today. It's always wonderful for us to hear about and sort of see where you all are from and interacting with us from on this event. My name is Dr. Sam McMaster. I am the content manager here at Surface Ventures, and we are a non-for-profit organization, and our mission is to provide world-class surface and material science education for both academia and industry. Today, in our mini-symposium, we will be having multiple speakers, as you can see on screen right now. Each speaker will be speaking for approximately 20 minutes with 5 minutes of questions. So what I would say to all of you is please have your questions in mind, type them into the chat. I will mark them, and we will go through each of the questions for each speaker immediately after their event. After their talk, after which we will move on to the next speaker. I'd just like to say thank you very much to today's partner, Optimal Instruments. Our final speaker, Felix Zach, will be joining us from Optimal to present some work from them. We will also be releasing some poll questions and handouts from Optimal Instruments throughout the event, so I'll be alerting you in the chat when those are available. We're planning to go for around 120 minutes in total today, and we will be sharing a link for your attendance certificates later in the event. It'd be great if you could post about that and tag us on LinkedIn just to highlight the work that we're doing with these events. So without further ado, I think it is time to welcome our first speaker and proceed with the webinar. So our first speaker today is Mirko Kroll of BOM. Mirko studied chemical engineering and worked for several years in the polymer industry. In 2020, he joined the Tribology and Wear Protection group at the Federal Institute for Material Research and Testing, which is the anglicized version of BOM. His work focuses on polymers, standardization, and digital infrastructures. Welcome to the stage, Mirko. Great to have you with us. I'll just take my slides off and let you get your screen share set up.
Yeah, let's hope that's working. Greetings from, well, it was raining a couple of seconds ago in Berlin. Now the sun is coming out for the webinar, so it's good. Greetings to everyone.
That's good to hear. Well, it's just started raining here in the UK, as is normal, so
maybe
there we go.
It was very fast.
Yeah, yes, I think we swapped weather.
Yeah. So thank you for the introduction at first, and thank you for the opportunity to present here at Surface Ventures. I think everybody can see my slides, hopefully.
Yes, I can see those, so I'll leave stage now. Please take it away, Mirko.
Perfect. Thank you very much. Okay, so let's start. Yeah, thank you for the introduction. Without further ado, my talk today is about harmonizing tribo tests of polymers and hydrogen. I work at the Federal Institute for Material Research and Testing. I will not pronounce the German name because it's too long. Just say BAM, not BAM. We are not exploding things on a regular basis. Anyway, this project or the presentation I will do today is part of the project together with the Austrian Competence Center for Tribology in Wiener Neustadt in Austria and the Leibniz Institute for Polymer Research in Dresden, Germany. So, yeah, why hydrogen? I mean, why this is important? First of all, hydrogen is impacting things, especially polymers. Hydrogen is absorbed as a molecule into polymers, and due to that, the mechanical properties of the polymer will change. And at the same time, some of those processes or some of those changes are reversible. So that means if you, well, let's say, put the polymer out of the hydrogen atmosphere, some of the changes will go back to the original, let's say, status or, yeah, property. At the same time, hydrogen also interacts with metals as an atom. So the process is completely different to polymers. And as we all know that the surrounding medium is influencing the tribological contact in general. So there is an impact of hydrogen onto the tribological contact. So we need to investigate them. Why? There are some applications that actually deal with hydrogen in a tribological sense. There are, for example, valves. You have some sealings there on valves that are made of polymers. The valve seals are sometimes made of polymers. There are hydrogen compressors outside the ceilings, for example, both static and dynamic, for example, for the shaft sealing. Actually, the things I will present today are coming from the application of hydrogen compressors, especially for the dynamic sealing of the shaft. And there are also hydrogen internal combustion engines, for example, for trains or trucks out there. And you have a lot of tribological contacts that actually come in contact with hydrogen. And also, you need to put the hydrogen into this machine. So you have fueling systems, and this is another completely own system of tribological contacts, also with polymers, sealings, etc. So there's a need, and why do we need to actually harmonize things? At first, we all know that hydrogen has been identified as a carbon-free energy carrier and storage medium. So that means that additional equipment and existing equipment that has not seen hydrogen before, for example, from all this gas infrastructure, natural gas, will come in contact with hydrogen, and we do not know how they perform in a hydrogen atmosphere. And at the same time, as I already said, material and surface property will change in hydrogen. And we at BAM, there's a competence center called H2 Safety, and this was introduced and created because there's a need to do a hydrogen test. And at the same time, the procedure you apply before and after the tribological test will influence the tribological results if you're investigating hydrogen. And we are, from our perspective, there's an increased request for characterizations in hydrogen atmosphere. And this is exceeding the testing capacities. So we need more infrastructure, and that means that you need to harmonize things because you get new equipment, and you need to make sure that they deliver the same or similar or comparable results as other machines. And at the same time, all those buzzwords, machine learning, artificial intelligence, digitalization things, life cycle analysis, they need reliable and comparable and especially reproducible data that are fair. So we need to harmonize things to make sure that they are comparable. And AC2T and BAM are part of the shared infrastructure for our Triboma, the European Tribology Center. So if you share infrastructure, you need to make sure that they deliver comparable results. Otherwise, the customer will not know what is actually true. So if we are talking about harmonization, we are, well, quickly in standardization. And the question will arise, are there any standards that deal with our things? And there's actually one. There's a Canadian American standard, which is actually a compendium of several things when you want to investigate the hydrogen influence of polymers. And one part of that standard is the dynamic wear. There's a tribometer unit described that is fully immersed in a pressure vessel. They're purged with argon prior to testing. They have a 12-hour saturation time, and they have a steel ball on flat polymer sample setup. And they determine where by weighing the samples before and after the test. And we are asking ourselves, well, is that covering our use case in tribometers? And we had to say, no, it does not. And if I talk about tribometers, then I will quickly introduce our stars, so to say. So the tribometers we use. The first one was the PT1 tribometer at BAM in Berlin. This is a high pressure tribometer that is able to test up to 80 bars. You can see here in this arm, there's the polymer sample that is clamped into the arm, and then the arm is put onto the steel disc, which you can see here. And this table is moving in a reciprocating manner so that there's, let's say, the tribological contact happening in between. And this tribometer unit is then introduced into a pressure vessel. Another tribometer we used in our project was an SRV4-based tribometer in Wiener Neustadt at AC2T. You probably all saw sometimes an SRV4 or SRV setup. So you know that, and what ACT was doing, they built an bellow, a rubber, let's say, balloon around the tribological contact where they introduce hydrogen into that, let's say, contact. And due to the fact that it's a rubber balloon, you can test up to, well, at atmospheric pressure or 1 bar with hydrogen. And then you can see here the polymer sample moving over the steel disc. And the last tribometer we used in our project was also an SRV4-based tribometer at BAM in Berlin. There, the BAM built, let's say, chamber around the contact, which was originally designed for hot water steam, and we changed that to hydrogen. And due to the, let's say, huge volume of that chamber, we are also just able to test the atmospheric pressure of hydrogen. The materials we used was a commercial one. The first one was a PHPV, which was provided by Mitsubishi, formerly Quadrant, which is a polyether ether ketone with 10% PDFE graphite and short carbon fibers. You can buy that. It's a commercial material. The next material we used was a PBS-based material, polyphenylene sulfide, with 10% PDFE and graphite, which is not really commercially available, but similar to some existing compounds. The last one we used was provided by the Polymer Research Center in Dresden, which is PA12 based. And the difference is it's not a physical compound as the first two. It's actually a chemically coupled compound. So the first step, you couple the oleoyl alcohol, which is basically an oil, with the PTFE in a chemical way. And after that, in a second step, you couple that oligomer to polyamide 12 to the matrix. So it's not a physical compound, it's a chemical compound, chemically coupled. And there were two different compounds we tested. Difference was here the type of PDFE. The parameters of our tests, all tests were done in a reciprocating manner, cylinder and disc. We tested for 1 hour at 20 newtons, which ended up roughly 5 megapascal, which is a typical contact pressure for sealings and hydrogen compressors and shaft sealings. We tested at 20 hertz with a stroke of 2 millimeters, as I said, with atmospheric pressure or 80 bars, depending on the tribometer of nitrogen and hydrogen. The temperature was at room temperature. We didn't regulate that, so that means we didn't heat and we didn't cool. The polymeric sample was a pin or cylinder with a diameter of 6 millimeters and a length of 10 millimeters with a milled surface. And the metallic disc was made of 316L with a lapped surface. And we did 4 tests per configuration per parameter set, which means 1 test and 3 repetitions. Regarding the load, just some words about the contact pressure, because this will change due to wear, because we have a cylinder, we're testing on the cylinder surface. So what we did, we used an FEM and an analytical or geometrical model to estimate the contact pressures. FEM model, you have some kind of grid, which is then parts of this grid is removed due to wear, and the analytical model, which is basically calculating the chord length and via that the contact pressure. If you like some formulas, there are some formulas, but this story is clear, I think. And if we did that, we figured out that after 15 minutes, both models actually converge to another. So that means they are both, let's say, comparable after 15 minutes. The wear volume and the time, of course, they are the same. And if you plot the contact area via time, you can see that they converge after 15 minutes, and the contact pressure at the end is roughly, here it's just plotted for 0.3 hours, so a third of an hour. If you extrapolate that to 1 hour, you end up roughly at 5 megapascal, which is the application. So at the end of the test, we are near the application we want to see. If you're talking about harmonization, we also, as I said, the procedure applied will influence the outcome. So that means we need to harmonize things regarding the sample properties and the manufacturing, the preconditioning, the cleaning, how to clean the chamber which you want to test by evacuating first or purging, the cycling purging, the saturation time, the pressure release. Some polymers are sensitive to rapid gas decompression, the desaturation time. And what I want to say with that is you need to harmonize things that are happening even before the test you're doing and after the test you're doing. So it's not just tribo test, it's also things before and after. And also things you need to harmonize is how to actually, because we have a reciprocating manner, how to actually evaluate the coefficient of friction and how to determine wear. Because we didn't do that by weight, we did another way. I will come to that. So these two things also needed to be harmonized, and I will say some things regarding that. Regarding the coefficient of friction, as I said, reciprocating manner. That means that we end up with a friction loop or an hysteresis. And this evaluation of this hysteresis to calculate the coefficient of friction is often done by the software of the tribometer. So you need to know how the software is actually doing that and not just saying it's a coefficient of friction, because there are several ways to do that. For example, the maximum coefficient of friction, where you take the peak of the forward or backward stroke, or the mean coefficient of friction, where you say the average of forward and backward stroke, and that is your coefficient of friction. There are other methods for sure, but those two methods were used by our tribometers. Regarding wear, we did something that probably a lot of people do. We did that with a microscope, so that means we ended up with a 3D topography. So we have a confocal microscope, or any microscope, you get a topography of the sample, and then you need to manipulate this topography to actually determine the wear volume. And the thing is, the issue why to harmonize things, there's no standard available for this process. So we used at BAM, we used the nanofocus, which is a confocal microscope I just said. At AC2T, there was used an Alicona, which is a focus variation microscope. And the variation was done via Mountains Map. A lot of you probably know that software. It's rather common, sometimes branded differently due to the manufacturer of equipment. We also compared two versions here, but the difference is neglectable. But the thing is, if you say to the operators, please determine the wear volume as you usually do, you end up with up to 33% difference between, let's say, different procedures at AC2T and BAM. So we saw, okay, this is an issue. We need to harmonize things, how ACT and BAM are doing things. And if you do that, for example, how to remove the shape, remove outliers to level the topography, we were able to reduce that to 5% different, which is not perfect, but much better than 33%. So harmonizing actually helps to make results comparable. Some frictional wear data of our PD1 tribometer of the compounds that we used. The mean coefficient of friction is plotted here, and we can see that not every material reacts to hydrogen and higher pressure the same way. So there's no general, let's say, rule that hydrogen is increasing or decreasing friction. The same goes for the wear volume, and you can see here there's a huge, let's say, standard deviation between the tests. So you mean, I said 4 repetitions, so this is the standard deviation of those 4 tests. And you see that the especially for those that are fiber reinforced, the scattering is rather high. So we all know that wear is somewhat tricky to reproduce for polymers. What you can see here, as I said, the medium and the pressure is not necessarily influencing the contact in the same way. And what we also did, that we had a look if the wear correlates actually with the model values. I've shown you the models before, and this actually worked out very fine. So the short length, for example, was the modeled one was actually coming very close to the test, to the actual wear of the sample. And I mean, we all know higher friction does not necessarily mean higher wear. For example, the PA12 materials from the Polymer Research Institute in Dresden, they have a rather high friction but very low wear. So this is good. When you want to compare tribometers, I need to hurry now a little bit. We are seeing here on the left-hand side the comparison between the SLV4 with the bellows in Austria and the PT1 at BAM. The friction is rather close, so I would say, well, it's just one data point, but it's safe to say that at least at that data point, both tribometers deliver comparable maximum coefficient of frictions. If you do the same thing for the 2 SLV4 type tribometers, the one in Austria and the one with the chamber at BAM in Berlin, you can see here that even the trends are different. So something is not comparable here. And at the moment, we assume that it's due to the ceilings of the chamber at BAM, so that those ceilings that the chamber is, let's say, enclosing the load application and the arm of the contact, that they will influence the result. So there's some more things to be done to make those tribometers comparable, and we are working on that. Another thing, the wear volume produced by the tribometers, again here for the SOV4 in Austria at the PT1 at BAM. So the wear at first glance, you can say, okay, well, the wear volume, there's huge standard deviation, as I said, but they look very close. But what I did, I had a look into actually the values recorded by the tribometers to calculate the wear coefficient, where you have the normal load, the actual normal load, and the distance over 1 hour due to the stroke, adding them up. And then you can see, they are not really comparable anymore. So the first glance may be misleading if you actually look at the recorded values of the tribometers. So I do not know right now why this is. Could be that the sensors are not comparable, or that there's something else happening, which I do not know right now. But the main story is, have a look at the wear coefficient, that might tell you something. So if we are talking about harmonization, we was talking about standardization, and we are working on that actually at BAM. My colleague, Dr. Geraldine Tyler, is leading an ISO standardization project that is actually trying or standardizing the process of polymer testing, tribological polymer testing in hydrogen atmosphere on an ISO level. And at DIN level, which is the German standardization organization, we've created at the beginning of this year a working group that is solely looking for tribological issues, not material-wise, but on a, let's say, tribological idea. And we have initiated 2 standardization projects. The first one is terminology and ontology, which is led by me. And another one is focusing on 3D wear volume, which I've just showed you, that there's a standard needed, led by my dear friend, Patrick Behr. So we are working on standardization to actually, let's say, provide something back to the community. And another thing concerning community is the tribology challenge. I've shown you some ways how to calculate the coefficient of friction, and there are several ways out there. And we are trying to, together with the community, together with you, to harmonize those. The first one was finished, and you see where, friction loops are 3D data. You have the displacement, the time, and the friction force. So I have a complex thing, and we want to put that into one number. And of course, there are several ways to do that, but we need to standardize and harmonize things together with iTribomat, here the University of Mondragon and BAM. And the idea is at the end to create a SEN workshop agreement to, let's say, provide at least a pre-standard how to do that. If you want to know more about that, feel free to scan that QR code with your smartphone, or just go to the homepage of iTribomat. You will find out some more about things about the tribology challenge. The second part will happen very soon, and you are warmly invited to participate. And another thing, another benefit, I really need to hurry now. If you harmonize things, you enable that you can share and store trusted and comparable data. So what we at BAM and AC2T did was that we used the infrastructure of iTribomat. So we store the comparable data in one database, which is provided by iTribomat, and then you are able to very quickly to compare a huge data set by just one mouse click. For example, if you want to see the influence of nitrogen on hydrogen, so you can actually do that very quickly and not with, let's say, complex things, searching all those time series together. So that's another benefit if you actually do that in a fair manner. Findable, accessible, interoperable, and reusable, sorry, which is fair. Okay, to quickly wrap up things, you need to consider the design and the software of the testing equipment. And no kidding, hydrogen is influencing the tribological performance. We need specific standardization for in situ tribological characterization, especially for polymers. And we need that we are able to make our results comparable, to actually reuse data. Otherwise, garbage in, garbage out, if they are not comparable, how to use all those machine learning, neural networks, and all those things if you are not sure that the data is close to the truth. And hydrogen, as I said before and after the test, adds another, let's say, complex parameter set to tribo testing, which is already complex, as we all know. So this is not an easy topic. And yeah, at the end of my talk, Thomas Wopelka, who will present after, well, the third talk actually, will tell you some more things about the hydrogen infrastructure at AC2T and other results. So stay tuned. He will tell you some more things. I will close that with some acknowledgements to the Polymer Research Center in Dresden, also the operators at AC2T at BAM and AC2T and BAM, because we were asking very tricky question and trying not to be too, let's say, too tricky, and to Ivan Delic, who was starting with the project and then left, but had a lot of things provided to this project and the things I presented. So we are still working on that. There's still a lot to do. If you're interested in that, scan that QR code with a smartphone. You have all my contact details there, or write them down. I'm there, and we'll try to connect with you. So that's basically from my side. I'm open to any questions if there are. I didn't see if there are some questions in the chat, but maybe Sam can help me with that. Thank you.
Absolutely. Thank you very much, Mirko. That was a fantastic presentation. We do have 2 questions, so if we'll take that, we'll do those 2 and then move on to our next speaker. Okay, so our first question is from Zenshu. I hope I pronounced that correctly. Apologies if not. And they ask, does pressure change the motion speed of the tribo pair during test? For example, at higher pressures, does it move slower?
Well, not in our case. The tribometers, I mean, if you increase the inner pressures, then of course you have some, well, at least for the PT1 tribometer. The other 2 tribometers were just testing at the atmospheric pressures, so there was no, let's say, difference in the outer and the inner forces on the ceilings.
Yep.
And the PT1 tribometer actually is put into the pressure vessels. So that means the pressure is all around the contact. So that also means that there's no change of speed. I cannot, let's say, generalize that to all tribometers out there, but in our case, it did not change the motion or the speed of the motion.
Thanks. I mean, I'd imagine that would only really be, or you'd hope it would only be a factor at really high pressures, but, you know, again, who knows? We got a question here from Sai Krishna, who asks, does hydrogen have an impact on the type of wear?
On the type of wear, okay, that's interesting. I wanted to go back to the diagrams, but I was not going into the type of wear, just the wear volume. So the slides do not help here. Anyways, to answer that question, not really. The conditions under our test, we had abrasive wear in all cases. So there was kind of an, let's say, the polymer was just scrubbed. There were no change of the, because the polymers were quite soft. There was no change on the metal side. There was some transfer film, of course, and we didn't see any change in the transfer film due to hydrogen or nitrogen. So in our case, for our polymers, there was, from my perspective, no impact on the type of wear, but as I said, the polymers are quite different due to the type, so this also cannot be generalized. So in our case, to make this very quick, this answer, sorry to be so extensive, it didn't have any impact on the type of wear. I hope that answered those questions.
No, that's absolutely fantastic. Thank you very much, Mirko. And thank you for again for your fantastic presentation. So it is now time for us to move on to our next speaker, Dr. Carlos Sanchez from Southwest Research Institute. I shall welcome him on stage now. Oops, sorry, Felix. I meant to click Carlos. Sorry. Carlos earned his Bachelor of Science, Master of Science, and PhD in Mechanical Engineering from Texas A&M University. He has been at SWRI for 8 years and works in the Tribology Research and Evaluation section, where he's responsible for project design, testing, and surface characterization. He also leads all efforts related to rheology at SWRI with extensive fluid analysis capabilities. Carlos is also highly involved in STLE. Welcome to the stage, Carlos. Great to have you. Okay, just noticed you're muted. If you don't mind unmuting, please.
Thanks, Sam, for the introduction. Let me
welcome.
Go ahead and share my screen.
Okay, thank you.
Hopefully this works here. Share.
Okay, looks like it's loading in now.
Can you guys see my slides now?
Yep, looks good, Carlos. Thanks.
All right, perfect. So, yeah, thank you guys for having me. And today I'm going to be talking about tribology testing in a hydrogen environment. Mainly be focusing on the method we developed to actually test in hydrogen for ring and liner applications, mainly for ICE applications. Mainly be going over the method we developed, the test rig we built, and just some initial results, just so you guys get a sense of what we're working on at Southwest Research Institute. Let's see. Why isn't it going? Apologies, my screen doesn't seem to be working. Let me do this again real quick.
Would you like me to bring up the other version of the slides I have uploaded on the platform, or just trying to do the?
Let me try it again. Sorry, I don't know why it's.
That's okay. Things, it happens. We'll have backup just in case. Apologies, everyone, just for the slight delay. Let me just release another poll question.
Okay, there it goes. Sorry, my slides got stuck for some reason.
There we go.
I'm trying to do two screens at once.
Okay, please take it away.
All right, thank you. Anyway, introduction. Kind of what Mikro just talked about. Hydrogen poses unique challenges in tribological contacts for many reasons. One of it being that such a small atomic particle, it gets into your surfaces pretty easily, pretty readily. It can cause issues in especially metallic surfaces related to hydrogen embrittlement, where it actually gets into the crystal structure and causes things like fracture or premature wear or stress cracking and so forth. It has very high diffusivity and permeability that leads to this type of degradation. It affects material properties and, of course, lubricant performance at various levels, depending on the material type and the severity in which the hydrogen is actually in that environment for those materials. As far as tribology goes, it can exacerbate wear, increase friction, or affect frictional performance. Have enhanced wear behavior, and also that induced cracking I mentioned earlier. And sliding and rolling contacts, such as roller element bearings, you have a higher risk of spalling and surface fatigue. So any kind of sliding and rolling contact, that's one thing to be aware of in a hydrogen case. Of course, you'll also have chemical reactions with hydrogen, depending on what materials are interacting with it. It can also affect friction and wear. So the goal as a tribologist, of course, is to address these challenges, to create a better understanding of how hydrogen is being affected in these different systems. And challenge in this case is being able to offer a test rig that can actually replicate these types of conditions. As Mikro had mentioned in his previous talk, there's not that many rigs available that can perform this type of work, and this is where we're trying to come in to kind of bridge that gap. So there's different strategies to mitigate hydrogen. Just like any other tribological issue, you can do things like change the lubricant formulation, select different materials, perform different surface treatments, and of course optimize system conditions by affecting temperatures, pressures, whatever your running conditions are going to be, to kind of mitigate those issues moving forward. So big background. So mainly focusing in the automotive side of hydrogen, doing H2 ICE applications. So hydrogen is very attractive in the automotive field because it offers very high energy density. Compared to gasoline, it's much more effective as far as a fuel. Of course, there's challenges associated with that. Regulations that have to be adhered to and so forth. Another issue is burning hydrogen at stoichiometric levels produces NOx emissions. So anybody familiar with NOx knows there's just challenges related to that in terms of tribology and also environmental concerns. As far as hydrogen combustion goes, one of the other considerations is the fact that hydrogen produces water as one of the byproducts, which can condense on different surfaces at low temperatures, so anything below 100 degrees C. And of course, water in any kind of system, especially mechanical system that has a lot of metallic components, can cause rust and cause wear prematurely in different areas, especially in cylinder walls for combustion reasons. In addition to that, the water can also dilute engine oil and other lubricants, just water from the blow-by, which affects viscosity and also promotes corrosion in that case. So again, tribological challenges would be the oil dilution and corrosion, and of course the embrittlement related to that hydrogen absorption in the surface. Quick background at SWRI. So at Southwest Research Institute, we have, we're basically a collection of different research areas that focus on different subjects and topics. One of those, we have a consortium essentially set up that does a lot of hydrogen research. I won't get into this too much, just to give you guys an idea of where we're coming from and where our expertise lies. We study hydrogen in all different aspects, all the way from production to the transport of hydrogen through pumps and physical transport, even to storage of hydrogen and uses of storage in different applications for fuel cells and ICE engines and so forth. If you'd like any more information on that, you can always visit our website at hydrogen.swri.org. If you're doing any work in things like hydrogen blending, hydrogen combustion, storage, compressors, and so forth, we'd likely be able to help you out on that. But that brings us into where we're in a unique case in a tribology lab to actually set up our lab to test in hydrogen. There's a lot of considerations you have to take into account when you're setting up a test cell that can actually test in hydrogen and building a test cell that can support hydrogen as a gas. So our objective primarily is to create a comprehensive understanding of hydrogen interactions in machine elements under friction and wear conditions, essentially creating a tribology test that's repeatable and reliable that can study the effects of hydrogen for tribology and lubricant performance and material performance. And of course, study degradation phenomena in PEM fuel cells. That's the proton exchange membrane type fuel cells, where it uses hydraulics exchange between hydrogen and oxygen as an example application. So our solution, one of our specialties as a tribology lab is coming up with new solutions to these unique problems, and we always take a systemic approach to designing different test rigs or different test procedures to meet these challenges. So in our case, we wanted to design an enclosed chamber around an existing tribology rig that's capable of supporting hydrogen in a very safe and reliable manner, and be able to offer, since you're talking about ICE, offer the same tribological tests that are currently offered by ICE drivetrains and materials and fluids, and leave it open for other applications as well. I mean, one thing we're getting into is polymer testing, but more on that, probably in a later presentation. So designing a test chamber for an existing rig, we have for ICE, we typically run we call ring and liner testing. So you take, in our case, you take a actual cylinder liner from an actual engine, we cut it into small coupons. A diagram of that is in the lower right-hand corner, where we take a full liner, we cut into these coupons, and we take the actual piston rings and run them against itself in a reciprocating style test. And for that, we typically use a Plint T77 reciprocating tribometer. It's a very common tribology rig. I'm pretty sure a lot of you in the audience have used one before or are familiar with this test rig. It's very versatile as far as reciprocating testing goes. It uses a mechanical system to drive the linear motion. So it's like a cam box on the backside. It's driven by a motor. For its automotive applications, it's fairly reliable. In this case, we use it pretty extensively for ring and liner applications. I have a lot of experience in that. And we wanted to design a chamber that enclosed a ring and liner type setup to be able to support hydrogen. So of course, there's a lot of design needs to be taken into consideration for that to make sure it seals properly, considering how this machine is driven. So it's driven externally with that motor, and then it translates linear motion inside of our chamber. In addition to ring and liner, the system we designed is able to support other contact geometries such as pin on flat, ball on flat, even on polymer on disc, and so forth. Basically, any type of test you can run on a T77, you can run it on the hydrogen setup that we have now. So with that in mind, we had to create a hydrogen test cell. Just getting into the safety aspects of hydrogen, we had to create a separate test lab for this. So we basically partitioned an existing lab that houses our hydrogen cell, where it's just sitting, test cell sitting on its own. All the electronics are outside the cell. We had to remove all the HVAC in that room and put, explosion-proof lighting, explosion-proof exhaust system, and all the electrical is just completely removed from that room. It has like a negative pressure in there, so in case there's a leak of hydrogen, it kind of expels and gets scrubbed outside of the cell. And everyone that needs to work in this lab is fully trained to operate the test rig and so forth. We have a whole procedure and that's available for this for our technicians. And like I mentioned before, we have extensive experience in testing hydrogen and working with hydrogen at SWRI. So we relied heavily on those other groups to help us set this up. So it's being able to be tested in a very controlled and safe manner. So everything is well taken care of in that regard. As far as the test chamber goes, I won't get into too much in the design, but to give you a kind of sneak peek of what it actually looks like. So it's a clamshell style design that fits around a T77 chamber. If you're familiar with the T77, the way that it measures friction, like the test rig itself sits on these stanchions, they're these little flexure bars that oscillate as you run your tests, and that produces that oscillation on a piezoelectric sensor that measures the friction coefficient. So it basically runs like a normal T77. The advantage here is that the friction is measured outside the cell, so we don't need to have any sort of sensors inside the cell while running the test. So there's a number of different seals that go into this to transfer the load, to maintain the oil and maintain the pressure. In this case, it can run at up to about 50 psi of pressure to maintain that hydrogen environment inside the chamber. Like I mentioned before, the T77 is like a two-part design where you have the cam box on the right side. It transmits the linear motion into the test cell. So there's several different sections that have linear seals, and it's all well encapsulated there. But other than that, it's able to run just like a typical T77. So you have dynamic loading, you have temperature control, you have that external friction measurement, and so forth. And we're able to run a ring and liner test in here pretty effectively. And it's fairly small volume. Well, 300 milliliters, I guess we consider kind of small. But you can fill it up with the lubricant. It has all kinds of plumbing, or you can actually pump the lubricant in and out of your system if you need to as well. So pictured here is just some CAD drawings of a cutaway, what that would look like, and then on the bottom is the actual machine components. You can see how many parts go into this. It takes quite a bit of time to actually set it up and make sure it's properly sealed. Here's just some more pictures of what it looks like. You can see there's all kinds of valves and ports going in and out of the system. So we have, in addition to the valves going in for hydrogen, there's also some pressure transducers that measures the pressure while it's running. We also plumb in nitrogen gas that's used to purge the system before and after each test. We also use the nitrogen to kind of qualify the system as well, to run tests in nitrogen to see if there's any effect, nitrogen gas versus hydrogen gas, and see if there's an issue there. As far as introducing the hydrogen, we're using a hydrogen generator. You can kind of see in the lower left-hand corner of that left-hand picture. So we're basically producing hydrogen on demand using DI water. So it uses the electrolysis method to produce hydrogen as we're running the test. So we're not using, hydrogen tanks in this case, although we could if we wanted to. We just wanted to, keep it as safe as possible and just produce hydrogen in small quantities, so that way you're not, running any sort of health risks and so forth, or safety hazards. So we basically run it throughout the test, and I'll talk more about how we're actually introducing hydrogen into the system to see how it's affecting the tribological performance of these materials. That's one thing we found is fairly critical and important in designing these tests. So here's more about the actual test setup. So the hydrogen generator is plumbed into the inlet port of the chamber. We have nitrogen gas plumbed into the chamber as well for purging, and there's also a separate nitrogen inlet that's plumbed into the back of the system, in this case in the cam box, because just in case there's any sort of leakage, if there is going to be a leakage, it's going to be leaking through the cam box side of the T77. That was the most challenging part to seal. Like I said, we have a series of linear lip seals that help to mitigate that leakage. But in case it does happen, we do have nitrogen plumbed in the back to kind of dilute any hydrogen that may escape. And of course, that is going outside into our scrubbers outside the room to make sure that's all taken care of. But yeah, there's several valves and connections that are located around the chamber to manage all the gas flow. There's also some pressure transducers there to regulate the pressure, or to monitor the pressure. And we have a specific procedure for purging and filling the chamber that all our personnel and our technicians are trained for, to make sure it's all safe and handled carefully. Here's an inside look at what the chamber looks like without the upper clamshell. As you can see, it's a typical ring and liner setup. We have our carrier arm at the top. The liner coupon is set up at the bottom. It sits on this little saddle piece that matches the curvature, the outside diameter of the liner, so that way it actually sits flat. And we just do our typical alignment procedure. If you've ever done a ring and liner type test, you know how difficult it is to get that kind of set up. We need to match the ring to the liner curvature fairly closely to make sure that there's even wear across the entire surface, so that you don't get any edge loading or center loading on the surface. Like I said, we have a lot of expertise in running that. We've run this test for years now, and our technicians are fairly well equipped to actually set this up. The chamber is filled with 30 milliliters of oil, whatever oil that we're testing with at the time. And there's a thermocouple at the bottom that can monitor temperature. We can run tests up to 100 degrees Celsius in this case. And like I mentioned, there's all kinds of O-rings and seals set up throughout the chamber that help keep the hydrogen in place. So I'll mainly be talking about the initial results that we had. We designed this chamber in for client project, so I can't go into too many details on the actual like oils that are used or materials that we use for this test. I'm just going to focus on how well the test actually works and how robust the chamber is. So here's an example of what this looks like. So test 1, we ran hydrogen at the start and the generator was turned off during the test. And then 2, we ran hydrogen continuously throughout the test. So one thing we found is that the way in which you introduce hydrogen to your environment is critical. Because hydrogen gets absorbed pretty quickly into your system, but it also dissipates pretty quickly as well. So if you just have hydrogen at the start without any kind of pressure kind of pushing it into your materials, it kind of goes away and you don't have any real effect on that. Whereas if you have it continuously flowing throughout your test, where you have the hydrogen actually flowing inside the chamber throughout this test here, you get more of an effect on friction performance. But throughout this test program, we looked at different methods in which to introduce hydrogen and whether it actually has an effect on these engine parts or not. So here's just a list of kind of the different things that we did to see, how well it would affect it or not. We also worked with other hydrogen groups to actually impregnate the hydrogen into our engine parts as well. So one method we did was actually put the engine parts into an autoclave with hydrogen for a certain amount of time, took them out of the autoclave and placed them in our cell. We found that the hydrogen actually dissipated pretty quickly and we didn't really see any effect, and it basically ran like a normal set of parts. So to actually see any sort of effect on hydrogen, you really need to basically soak it in hydrogen. And by that, I mean, have the parts sitting in the chamber fully flooded with hydrogen for, in this case, 3 hours. We did several different time frames for this, up to even 24 and 48 hours. We found that within the 3 hour mark, it's where that seems to be the kind of the critical point. So we left it at 3 hours. We also looked at either bubbling hydrogen or pumping hydrogen through the oil. So in this case, putting the inlet port at the bottom of the chamber to where the hydrogen comes through the oil, versus having the inlet port being at the top of the chamber where it just kind of saturates the environment where the parts are sitting in. So within all those different methods, we found that soaking the parts in hydrogen for 3 hours prior to running the test, and then having the hydrogen actually flow through the oil during the test caused the most severe cases. So that's one of the things we're looking at. One thing to mention, though, there's a lot of debate on whether or not, in hydrogen ICE, if it's going, the gas itself is going to have, issue, whether it's the gas or the water that's being produced. I'm not really here to debate all of that, whether it's creating the real case scenario inside the engine. We're just trying to, prove whether or not, hydrogen itself is going to cause any sort of tribological concerns, and that's what we're trying to replicate here. So you could argue that, the case that we're presenting, having it soaked in hydrogen and going through the oil in these very severe cases isn't the real scenario in the engine. But the main thing is that we're able to recreate those conditions in our test cell. So if that is the case, we can actually set that up here and prove that, it will have an effect on your friction and wear performance. So getting more into the test results. This is a fairly messy graph, but I just wanted to show you, give you an idea of, tests with and without hydrogen. So we tested with hydrogen here, which are all the higher friction. These are plots of friction coefficient over time for a 6 hour test. Like I said, with that 3 hour prior soaking for the hydrogen, and then we ran the test here. For the test without hydrogen, there's a mix of ambient conditions. There's also a mix, and also some where we ran pressurized with nitrogen just to see if there's any issue there. But in either case, either without the hydrogen in ambient or with nitrogen present in the atmosphere, in the environment for that cell, we didn't see a significant jump in friction coefficient like we did with the hydrogenated test that we saw here. Getting to look a little more closely, here's a breakdown of a couple different methods we used to introduce hydrogen. So H2 soaked for 3 hours and hydrogen flow throughout the chamber. That's the upper graph there, that black curve. So you can see that that's probably the worst case scenario as far as introducing hydrogen. So you can see that the friction coefficient is a lot higher there. The next graph down, again, soaked in hydrogen and bubbled through the oil. So again, it's fairly similar. So the main part is just having it soaked for 3 hours for your parts and have a continuous flow of hydrogen throughout your system, either through the oil or in the environment. And then let's see, the lowest one would be that blue curve there, would be hydrogen soaked for 3 hours and then no hydrogen, where we basically turned off the system. It's still a higher friction coefficient, but you can see how it drops off. But in a lot of cases, depending on how the hydrogen actually interacts with your surface, you'll get kind of an erratic behavior, which you kind of see pretty frequently through looking at these friction coefficient curves. And we ran, like numerous repeats and of the same type of conditions, and saw that running with hydrogen, it's not as repeatable as running it like in the standard, like in open environment type setup. But in all cases, you'll typically see a increase in friction coefficient, whether it's a smooth curve or a kind of erratic curve like you see in that orange one there. Looking at the wear, so like I said, one of the critical things in doing a ring aligner test is the alignment. So you can see we have pretty good alignment on all of our tests. There's no edge loading, no center loading. It's fairly even wear across all surfaces. When doing the more severe cases with hydrogen, you can see that there's a little darkening of the surface. So most of this is all abrasion. There was a question earlier in the previous talk, what type of wear are you seeing? Mostly it's going to be abrasive wear. We did also look at SCM and EDS images or measurements of these surfaces, and we didn't really see any embrittlement or any sort of damage related to like hydrogen. It's mostly what you would see for just typical abrasive wear for a ring and liner environment. Just in the hydrogen case, it's a little bit more severe. It's more like running the test for a longer period or at higher loading than normal. And just go back. So I forgot to mention the test conditions that we ran. They're kind of in the corner there. So we ran at 20 hertz frequency, 20 millimeter stroke, 200 Newton load, and 100 degrees C in temperature. For those who are wondering what the test conditions were. Looking at the rings, you can see there's a little more wear on the rings on the left side. Those are the ones that were the more severe hydrogen case on the right. And then we also did some measurements looking at white light interferometry to see if there's any more severe cases. So here is hydrogen being soaked for 3 hours, and this case bubbled through the oil or running through the oil. There's a little more dip on the reversal points, a little more wear on that side than the parts that were soaked with soaked for 3 hours with no hydrogen running through the test itself. So I know it's kind of brief on talking about the test results, but I just wanted to present, how our system is set up and just give you an initial idea of, type of results that you would expect to see. So in summary, we designed this new test chamber as capable of supporting hydrogen in a tribological environment. In this case, ring and liner, but it can also be used for pin on flat or any type of other test geometry for your typical reciprocating type test. We ran several ring and liner tests for hydrogen for an ICE environment, and we determined that the method in which you introduce hydrogen into your system really affects the results. So if you're really trying to force hydrogen in there, then you'll see results. But in a typical case, hydrogen tends to dissipate really quickly. So even if you have your parts sitting in an autoclave, under pressure and hydrogen for, a few days, you take them out of there, you're not going to see too much of a difference. You really need to kind of pump the hydrogen in. One thing we didn't really study, I didn't present here, is the effect of condensation or water, but we did do some of those tests there, and they'll probably be presented at a later talk. Like I said, but work is ongoing to test different ring and liner materials and different fluids that may be formulated to better support the hydrogen environment. But overall, our test cell has proven to be fairly robust. What's good is that it's a fairly large chamber that can do, ring and liner experiments as well as other test geometries. It's fairly reliable, fairly repeatable. And right now, we're actually working on a variation of this chamber that's being able to support ammonia testing. So look for that coming pretty soon. And with that, I'd like to end. So I have my contact information here. Our lead tribologist is Dr. Peter Lee. Those in the audience are probably familiar with Peter's work as well. So I work alongside him in the tribology lab and also doing some rheology testing. So that I would like to end my presentation and open for any questions that you all may have. Thank you.
Fantastic. Thank you very much, Carlos. We have 4 questions.
Okay.
Well, actually, just another 5. So let's see what we can get through before we need to move on to our next speaker. One from David here, who asks, "Is the humidity of the gas measured or even controlled?"
So that's measured primarily through the generator itself. It has a humidity monitor, so it keeps it such that it's able to actually produce hydrogen. Within the chamber itself, we do not measure humidity directly. We just purge it with nitrogen gas for a few minutes, and we just assume that it's very relatively low humidity inside the chamber. Yeah. But that's definitely something you could, easily add to it if you're interested in doing that.
Okay, thank you very much. So, yeah, David, if that's something you want to explore, you can get in touch with Carlos further. Question from John here. This is quite good. It's quite good. Hydrogen is the champagne of fuels. Why burn hydrogen in an ICE? It's inefficient.
Yeah, I guess you can argue it's inefficient, but it's mainly just due to its power density. Like I mentioned before, I mean, there's a lot of research being done on, using it for ICE. At Southwest, we have we're working on different vehicles for using ICE combustion. It's just an alternative fuel source that has proven to be, like I said, very energy dense. So it's you get more out of it than typical gasoline application.
Okay, thank you. One from Jameson here, who asks, what were the lubricants used? Did they have an additive package? And if so, was the interaction with particular additives considered?
So these were, so we worked with the client on this. I can't say exactly what was in there, but they were fully formulated. I believe they were 5W30 style oils. But yeah, they were fully formulated oils, yeah. Okay,
thank you very much. A question from Dr. Chandra Shekhar, who asks, can hydrogen impact the solid lubricants performance, which used in the lubricants and also reinforced composites?
Yeah, that's a good question. Personally, we haven't looked at that, but I would assume that there would be some effect, but we would need to run some tests to actually verify it, but I can't say for certain.
Okay, thank you. And we'll do this question from Gregor as our final one before moving on to our next speaker. Gregor asks, thank you for the presentation. Could you give an insight into what material classes your results refer to?
So the materials themselves, they were just typical like carbon steel for the ring liner components. So just from a typical diesel engine, those are the parts we took them from. So they're chrome coated rings and yeah, like a carbon steel for the liner materials. I mean, if you want more information, you can feel free to reach out to me. I can give you some more info on that. But I can't really say too much about the lubricant because we're working with the lubricant company, so I can't say what was actually in them. But,
yeah. Of course. Thank you. Okay, thank you very much, Carlos. I think now's a good point for us to move on to our next speaker. But fantastic presentation. Very much enjoyed that. Thank you. Okay, our next speaker is Dr. Thomas Rapelka, who is a senior scientist and project leader at AC2T Tribology, at AC2T Research. His work focuses on nanoscale wear analysis and using radioactive tracer isotopes and tribological testing of hydrogen-exposed systems. He holds a PhD in physics and has over 19 years of experience in R&D. Great to have you with us, Thomas. Okay, would you like to please share your slides and then we will get going?
So thank you, Sam, for the nice introduction, and thank you for the possibility to give my presentation here. Can you see the slides actually?
So I can see the screen share. There we go. The slides are up. Brilliant. Please take it away.
Okay, I think now it should work, yeah?
Yes, all good. Thanks.
I'm giving my talk on behalf of Andreas Nevelsack, who cannot participate today, unfortunately, but who is more or less organizing the strategy behind our fiber testing investigations. As already mentioned by Mirko and Carlos, there's a strong motivation to use hydrogen because it's a promising future energy carrier in specific sectors. However, it comes with a lot of effects on tribological contexts throughout the whole H2 value chain. It can be present in different aggregate states. It can be under high pressure. It can be liquid. Depending on the aggregate state, it can be hot or it can be very cool with low temperatures in case of liquid hydrogen. It can be pure, it can be present as gas mixture, and it can be contaminated. Yeah? And all this has effect on the tribological contact and behavior. So it's actually challenging for materials and lubricants. With a mixture with oxygen, it's explosive. So there's a need of new characterization and R&D environments. So as already mentioned by the speakers before, it has an effect on the material and lubricant behavior. So this causes a reliability and lifetime issue. It can have an influence on the frictional and wear behavior. For example, by preventing or removing an oxide layer in metals, which is usually formed with present oxygen. So this might be prevented in hydrogen, in pure hydrogen atmosphere. It can cause special wear and failure mechanisms like hydrogen embrittlement in metals, swelling of polymers under high pressure. It could cause interfacial delamination of coatings. It can have effects on the lubricant, can cause special degradation mechanisms. And as already mentioned, typically applications are valves, sealings, compressor parts, which can be dry lubricated, H2 powered combustion engines, and it can also be used as energy storage resource to store energy, which is produced by electric power plants during the day, and the energy is stored as hydrogen in tanks, and all the pipes and storage tanks might be affected by hydrogen as well. We actually got a new building which is equipped with new laboratories, and these laboratory rooms are conformed to H2 because you need a lot of safety precautions and gas sensors and so on to run hydrogen research safely, because it forms an explosive environment with oxygen. So our whole equipment comprises a lot of different methods. So first we have tribological testing performance tribometers, so which can be run under hydrogen atmosphere. We can expose samples to hydrogen under high pressure, which is used to simulate long-term exposure and cumulative damaging. We can actually measure the uptake, or try to measure the uptake of hydrogen during the storage or a tribo test into the materials. We try to test the hydrogen formation during the tribo process in lubricants or from lubricants. And of course, we have some post-exposure and tribo testing diagnostics, which can investigate the samples after the tribo test. So first, a short overview about the tribometers we use. So the first one is an SRV5, which probably will be shown in detail afterwards by Felix Zack. So this is produced by Optimal Instruments, and the SRV5 is a very common and well-known tribometer, but now it can be equipped also with the H2 tribocell, which can be run up to 100 bar hydrogen pressure and up to 150 degrees Celsius, and with the common stroke and frequency range an SRV5 tribometer provides. At the moment, it's equipped with a bar on this sample holder, but probably it can be also equipped with pin or cylinder samples. This is maybe under development. Felix will probably tell more about this. And just a short overview. You have here the tribo contact with the bar on plate contact, and this small chamber is actually put under high hydrogen pressure, and this hydrogen chamber is surrounded by another chamber which is flooded with nitrogen to prevent any leakage of hydrogen, because this could cause safety issues. The next one is more or less a hydrogen chamber we produced ourselves. Mirko already mentioned it. We use a rubber or elastomer chamber which surrounds the tribo contact, and we mounted this elastomer chamber in an SRV5 tribometer. And since it's a rubber bulk, we can only run it up to ambient pressure, so it's not possible to run it up to high pressure as the tribocell produced by Optimal Instruments. But the cool thing is that we equipped this setup with an conventional mass spectrometer, and we can measure the outgassing of lubricants or the reaction products of a lubricant during the tribo test with the mass spectrometer. So this is actually a very interesting topic. It can be run under different gas atmospheres, and we also use the system to control the gas mixture during the tribo test to check if there's any contamination or if there is no explosive gas mixture formed. The next tribometer I want to show is called linear oscillating tribometer under gas atmosphere. This is constructed by AC2D ourselves. So the short version is Lotuga. It's driven by crank drive from a real compressor, which provides a bigger stroke than the SRE and the bigger sliding speed. It can be run until, up to 190 degrees Celsius, but again, it can only be run at atmospheric pressure and not at higher pressures. You can see on the right side the crank drive, and on top of the big box there is the actual test cell, and I think you have the pointer option here. You have here the test cell, and the crank drive drives a rod which is moving vertically up and down. This is actually the green part here in this sketch, or you can see the rod also here in this schematic drawing on the bottom. And on these rods there are two plates on each side, and these plates move upwards and downwards with the rod, and from left and right. In this case, it were polymer samples were pressed onto these plates, and this is where the tribological contact occurs. And this chamber between the plate and the polymers can be flooded with hydrogen, air, or even or nitrogen. I want to give you first results or investigations we did. So the application here was to test materials for high pressure and dry hydrogen piston compressors. I have to mention the first tests were done in nitrogen atmosphere, but testing in hydrogen atmosphere is planned as the next steps. We investigated polyphenylene sulfide with different PTFE concentrations, which was reinforced with carbon fiber, which is a candidate material for piston rings in hydrogen compressors. So the PTFE was acting as a dry lubricant. You can see the test parameters we applied below, and there's also a publication I want to refer to when you're interested in more details. So the first results we got under nitrogen atmosphere is, you can see on the left side, the coefficient of friction curves throughout the tests. It was run up to 16,000 or 17,000 cycles. And the upper left graph is showing the results for the PPF with 5%, then 10%, and then 15% of PTFE. As you can see, the running in process, we had a higher coefficient of friction for the low PTFE concentration, but throughout the test, the coefficient of friction was evolving in the same way. So at the end, there was no difference at all anymore. We also measured the wear of the polymers at the end, which could not be distinguished statistically. However, the wear rate after running in was different, and the PTFE with 10% actually showed the highest wear rate. And what was remarkable also interesting is that the Mechanical strength of the PPS with 5% PTFE was much better than for the other tested polymers. So what is important is that you also investigate the H2 interaction with greases and oils. So we also have several methods to do this. First thing is actually a quite simple method. You just store the samples you want to investigate in a high pressure cell. This can be solid samples, greases or oils, with the goal to influence or damage the investigated samples. We can do a rapid or controlled decompression via needle valve, and this is interesting because you can test the destruction of polymers due to rapid decompression tests, for example. The cell can be run up to 1000 bar. The cell dimensions are quite small, so we can store only a very small test specimen in this high pressure cell. The next method is interesting to investigate the hydrogen uptake or gas uptake into greases and oils. So the working principle is that you fill the pressure tank on the right side with the gas you are interested in. It can be filled up to 200 bars of gas pressure. And in the left cell, in the pressure reactor, you fill the lubricant you want to investigate. And once this is done, you open a valve between these two tanks. And these two tanks are more or less then under the same gas pressure. And over time, you will realize a pressure drop in the tank system, and this pressure drop gives you information about the gas uptake into the lubricant. What we also do is we do artificial oil alteration of the lubricants we investigate. So we can see here a reactor device. This is a chamber which you can fill with the lubricant of interest. And through this lubricant, you can flush different gas mixtures. You can flush it with air, with oxygen, with NO2, SO2, H2, NH3. You can use up to 4 different gases at the same time, and you can also dose in 2 different liquids to this chamber. And due to the heating and the mixture of these gases and liquids, the lubricant ages and changes its properties. One sensor applied is an online corrosion sensor, which determines the effect on the corrosiveness of the different gases you apply to the lubricant. And after the test, you can take out the lubricant and investigate the properties like total acid number, total base number, the viscosity changes due to the alteration process. Further equipment we got recently is the Devanathan-Sakursky cell and the thermal desorption spectrometry. Just a short overview about this simplified version of the Devanathan-Sakursky cell, which is used for determining the diffusion and permeation of hydrogen through materials and coatings. Thereby, it supports the investigation of hydrogen embrittlement, the investigation of barrier coatings to prevent hydrogen diffusion, and maybe you can also measure the effect of a wear track on the hydrogen diffusion of a specific sample. So you can see on the right side, on the top, you can see here a chamber which is filled with electrolyte, and the two parts of the chamber, so the left side and the right side, are separated by a membrane, and this is the material you want to investigate. In this case, it is the steel membrane, which is coated with palladium on the surface. On the left side, you flood the chamber with gaseous hydrogen, and the hydrogen is dissolved in the electrolyte and then diffusing through the steel membrane towards the right side, and the atomic hydrogen is oxidized by the palladium coating, and it creates protons. And on the right side, you have three electrodes. One is the steel membrane itself. This is the working electrode. Then there's the counter electrode, this is the platinum electrode, and there's an additional reference electrode, which is, I think, manufactured of silver chloride, which is used to adjust the potential of the working electrode. And by measuring the electrical current between the steel electrode and the platinum electrode, you can determine the hydrogen content, which is proportional to electrical current, and thereby you can determine the diffusion coefficient of the steel by determining the breakthrough time through the steel membrane. So the time the hydrogen needs to diffuse through the steel is an indicator of the diffusion coefficient. And how do we investigate the hydrogen embrittlement with this setup? You have to run two consecutive tests. You can run one test maybe today and the other one tomorrow. Once you loaded the steel membrane with hydrogen and you redo the test on the next day, the diffusion coefficient or the breakthrough time might change. So if the diffusion coefficient is much higher than the day before, it's an indicator for formed traps in the steel sample, which is an indicator for the hydrogen embrittlement. And this can be also confirmed with some X-ray analysis after the testing. So if you're interested in detail, there's a publication which I want to refer here, and the whole process and setup of the Stakursky cell and the results are presented there. And the last equipment I want to show is this thermal desorption spectrometry. The application is the analysis of reaction mechanisms, degradation mechanisms of the samples you investigate, or the loss of content of volatile substances. In principle, it's a chamber where you put your sample. This chamber can be heated up to 1400 degrees Celsius. And the chamber is equipped with a very accurate scale with high resolution, and you measure with thermogravmetric analysis the weight loss of the sample on this scale. And simultaneously, you can do some differential scanning calorimetry, where you measure the heat flux towards or through the sample during the heating process. And these two signals allow you to determine the reaction mechanisms or phase transitions in the material you investigate, if you have a good knowledge of the material yourself. Without knowing anything about the material you investigate, it will not be possible. And we also equipped this TDS system with a mass spectrometer. And with the mass spectrometer, we can detect, for example, the outgassing of hydrogen of samples that have been stored previously to the investigation in DTS in hydrogen with high pressure. So this is the result I want to present you. Actually, it has been measured a few days ago. So I got the results this week and they are quite interesting. That's why I want to show it. We investigated here this PPS polymer with PTFE particles and reinforced carbon fiber. 4 samples were stored in a high pressure hydrogen cell for a week with 100 bar pressure. And then the samples were removed from the hydrogen storing device simultaneously and were just stored in air for the next time. And we did a series of TDS measurements with mass spectrometry on those samples. And these 4 samples were measured in different time steps after removal from the cell. So the first sample was measured after 33 minutes, the second after 127, the third after 220, and the fourth after 330 minutes. So they were exposed to air after removal of the hydrogen storing device. What you can see in the graph is over a time period of 36 minutes, the TDS temperature was increased from 30 degrees to 300 degrees Celsius, which is the class transition temperature of this PPS material approximately. And at the same time, during this process, the hydrogen concentration was measured with the mass spectrometry. And as you can see, the hydrogen, the sample measured at first, after 33 minutes, shows a much higher hydrogen concentration, outgassing to the TDS and mass spectrometer than the later samples. So that means that this outgassing is a very quick process. There's a significant decrease of the hydrogen concentration in the sample over time after removing, which means if you want to do investigations on those samples, it's very time critical. So this has to be considered and taken into account when you investigate such samples. Just a brief summary at the end. We have a lot of trial testing infrastructure dealing with all the influencing factors hydrogen might cause. We have the tribometers, we have high pressure storage cells. We investigate also the lubricant alteration, and we also apply this with additional chemical analysis. So for getting the whole picture of the influence of hydrogen on the tribological performance. So thank you very much. If you have any questions, feel free to ask me.
Thank you very much, Thomas. Yeah, very impressive testing capabilities that AC2T have. We have one question at the moment, which I'll read out, and then then we can see if any other audience members have any questions. So this is from Frank, who hopefully I'm pronouncing that correctly, and they ask, can this de Vanathan-Starkowski cell also be used for hydrogen and gas mixtures?
Good question. I'm actually not an expert on this method. I think the diffusiveness of other elements might be quite poor, and the diffusion through metals those might be very slow if actually there's any diffusion at all. So it has to be present as in an atomic state to diffuse through the metal membrane, and probably I think you will not get any results for other gases.
Yeah. Okay, got it. Thank you. Does anyone else have any questions for Thomas? We have a couple of minutes we can spend to have some further discussions. If anyone else has any other questions. Or if perhaps Thomas as well, if there's anything you want to kind of further elaborate on from your talk, we can take a couple of minutes to do that. Otherwise, we can look to move on to Felix.
Yeah, I mean, as mentioned, I think to investigate the effect of hydrogen on the tribological contact, you have to look at the whole picture. And, yeah, you have to use a comprehensive approach, actually.
Yes. Absolutely. So I think, thank you very much. I got a question from Michael, possibly. Apologies if that's pronounced correctly. They ask, what is the material of the cell itself?
I think the Devanathan Sakursky cell is made of some aluminium alloy. As far as I know. Yeah.
Okay, fantastic. Thank you. Right, yes. So I think in the interest of time, just because we have one final speaker, I just want to say thank you very much, Thomas, once again for your fantastic talk. And we'll invite Felix on stage now to give the presentation from Optimal. Thank you. Okay, so Felix Zach is currently a development engineer with Optimal Instruments. He comes with a variety, a whole bunch of different experience from his BEng project of elastomer compatibility with various lubricants under dynamical load. Took part in a European project semester with Universitat Politècnica de Catalunya Barcelona Tech, the project being energy saving and air conditioning systems using hollow fiber membrane. Currently undertaking an MSc in aerospace engineering at the Technical University of Munich. Is an academic, or has been an academic tutor in mechanics, finite element coding, and physics, and has also undertaken a scientific project TUM on a multi-physics modeling, VHL line context based on Navier-Stokes equations. Fantastic to have you with us, Felix. Just before you begin, just notice you are muted, but please take it away.
Thank you very much for the introduction. Hope you can hear me well. And thanks for the opportunity to speak today. And big thank you in general for organizing such events.
Yep, coming through loud and sorry, Felix, just saying coming through loud and clear, and I can see your slides. So please take it away.
Okay. Welcome everybody as well. So today I will guide you through that topic points, and yeah, just go quickly through it because evening is coming close. First of all, the introduction and need. The previous talkers, presenters already show you that there is a big need for such an device or for investigating in that field of So tribological systems are complex. The outcomes of that are not just dependent on the materials and the lubrication that are used, also on the load collective. And this is why we meet today, because of the influence on the environment. And the previous speakers already show you the need for that. This is why I go quickly through that. These are just some papers and scientific works that has been done in that field. I will not go into detail of that here, this work was already mentioned by Mirko. And yeah, so we come to the development challenges when we want to develop a pressure tribometer for hydrogen applications under pressure. We need to deal the challenges that comes with the pressure. First of all, pressure creates a force acting on the area of that. We need to account for that. When we want to apply a wide temperature range, what is usual for our tribometers here at Optimals, we need to account for the ideal gas of law of gases. And also when we want to apply some kinetics to activate our tribological processes, we need to account for our stroke and the frequency. This comes with a pendulum effect. You will see later why this is placed here. And dealing with high pressure, we need to deal with the pressure vessel regulation, which is shown here. They separate the requirements regarding the safety into separate clusters depending on the pressure value and the pressurized volume. Dealing with hydrogen, all the challenges that coming with that are highly related to the unique property of hydrogen being the smallest available molecule or atom. Means due to Graham's law, which says us that the diffusivity of a molecule is dependent on the 1 over the square root of the molar mass. So this is why hydrogen is very diffusive. Also, due to the low energy that is required, that hydrogen dissociate on the surfaces to atomic hydrogen and then permeate through the material, and also can accumulate there on ground grain boundaries or on pores or yeah, in general imperfections, and yeah, leads there to a blocking of the sliding layers within the materials, and this will lead to an embrittlement, and yeah, so the loss of ductility. And also when we want to measure the pressure, here you can see an example of a signal drift due to hydrogen, because the hydrogen can permeate through the thin membrane and can change the properties of the liquid within the measurement device, and this is an irreversible process which leads to a signal drift, which we want to avoid. And also what was mentioned a few times before, and why we want to deal or use hydrogen for our energy change, because of the high energy density, we have to face the explosiveness of hydrogen when we have hydrogen available, and also a kind of injection. Now to solve all these issues, the first thing to solve for regarding the embrittlement and the permeation, just use the proper material, and yeah, for the embrittlement part, some kind of steels are already prepared for that, and for the permeation you need to apply some additional permeation tests to choose right polymer for sealing that. The measurement industry for pressure devices are already known for that issue there, and provide a solution for that, which is namely coating the device with gold, so prevent the membrane from permeate some hydrogen into the liquid which lays behind that membrane there. For the pressure, the first thing very easily to counteract for the force due to the pressure, we have a very trustable equation for that. We know the area which separates the pressurized and the not pressurized spaces, so we can account for that very easily. For the regulation part, we want to reach a pressure up to 100 bar. That means we need to minimize our volume to a specific value to lay below 25 bar liter to don't have the need of additional safety aspects and so on, and to be on the safe side. Now the other two topics are solved together with the other two topics of the previous challenge slide. The diffusion, we want to get rid of that issue by housing, obviously, the hydrogen, and this will look like that. You see here several kind of sealings, and due to the small size of hydrogen, it's very hard to seal it under dynamic conditions, plus pressure difference, which leads to that we apply a safety gas around our hydrogen gas, namely nitrogen, on the same pressure level to get rid of the pressure difference. Here on that table, you see the different sealing types. So first, number one, the static here, which separates the nitrogen and the air part, is very sensitive to the groove geometry. Here you see a small video of how such an sealing acts. First, we have a compression due to the mechanical stress, and then when we apply a pressure, you see the second deformation, which increases the contact area, which will lead to a sealed system. The next sealing type you see here is very sensitive to angular distortion. This comes to a conflict with our pendulum movement, which leads to the necessity of applying a special mechanism of a special kinematic mechanism, which is shown here. You see there we stay we keep the orthogonality of the kinematic axis here and the load axis here, and for that we are safe regarding the sealings type 2. When we apply such a mechanism, we need to also take into account some contact mechanics here for the pendulum to make sure that we are that the initial wanted movement is correctly lead to our contact down here. And also our belly here, which separates the hydrogen and the nitrogen space, will cause a parasitic force, which we need to be aware of, like Mirko mentioned, that such parasitic forces can change the signal of the friction, and to get a clear and comparable results, we need to account for that as well. So to avoid some explosion, we go the way that we try to avoid the existing of every three parts, means the fuel, oxygen, and the injection. By first of all, we have our neutral state where we have oxygen in the system. So first of all, we purge this system with nitrogen in both chamber so that we don't have any molecules of oxygen in the system. After that, we pressurize the inner volume with hydrogen. And in case of any safety issues, the system get automatically in an evacuation state. This is controlled by the safety device, the SPS in German. So the design and feature of the whole chamber looks like that. You are familiar to the SRV platform. We have our rotary guide up here, our extension of the drive arm, which is seen here, and the pressure cap is below the purple chamber here, and we have some temperature measurements to once control the contact temperature, and the second one here is to control any temperature rise that occurs during the test, which will maybe harm our ceilings. So if one of the temperature sensors measure a temperature up higher than 150 degrees, we will go into the earlier mentioned safety evacuation state. And also we have here some gas detectors that if there are some leakage of our chamber, this will be detected by that detectors. And we also go into the safety standard part. And also what was mentioned by Thomas, that we have different kind of contact geometries. Here we can apply a normal ball of 10 millimeters or line contact, also parallel contact using a pin, and ring on area will be also possible. On the back view of the chamber, you see any devices that are dealing with the gas supplying. From the front view, from the upper view, you see here the two circles, one's for the nitrogen and one for the hydrogen. And in the middle of that, we have the connecting valve, which is there to connect and to purge the inner volume with nitrogen, and in some safety situations also to get rid of all the hydrogen within the cell. For installation, and when you're in the joy of already owning a SRV, the retrofitting of such an option will last 5 to 6 days, roughly estimated. And when you want to change during your daily work from one option, like oscillating measurement without any special atmosphere, to one with a special atmosphere, this will cost you 2 to 4 hours, because it's also recommended that you calibrate the system when you do such a change, because of some changes that can occur in the whole system. And when you want to change the specimen, for the lowest specimen, this will look like that. maintain the upper specimen and the lower specimen. The upper specimen, you need to grab the chamber, change the ball, for example, here, and then set the chamber back into the system, and then mount all the screws and so on. And then at the end, you need to set up the oscillation axis, and this will last, depending on the skills of the operator, from 30 minutes to 1 hour. And to sum up the talk, I show you a short demonstration video of actual the pressure measured behind there will be tracked and recorded within the software. This was just during the development process. And that's for it. Thank you very much for the attention. And if you have any questions, I would be glad to answer that, or try to answer that. Thank you very much.
Thank you very much, Felix. A very comprehensive presentation on the hydrogen cell available from Optimal. We don't have any questions current. There we go. Got a question there from David. Before I read that out, I'm just going to make the attendance certificate available for anyone who would like that. If you please go ahead and click the link that is on screen for that now. The attendance certificate is only available now from this event, just to show that you have been here live. So please go ahead and click on that. We're not ending just yet though, so please go ahead and open the tab. The certificate will be available for the next day, so you won't have a big rush to actually complete the actions in that link. Right, Felix, sorry, let me read out this question to you from David, who says, in the first presentation, we saw that it is important to specify which coefficient of friction is reported, e.g. mean, maximum, etc. Which value does your test rig typically provide? Tell you what, shall we, there seems to be a few questions in this. Would you like to answer that one first, and then we'll go to the next one?
Yes. So the SRV normally provide every kind of COF you can calculate after the signals. So you have to choose what you want to get. So I recommend there not the maximum, because it's overlapped by the seal forces, and also maybe the displacement of the belly can manipulate the maximum. So better is some integral values.
But as I understand, excuse me, in the data analysis / software display screen, you're able to toggle on a number of, basically as many different signal processed values as the instrument provides. So as you say, you can you can select however many values are useful for the particular analysis you're doing. Is that correct?
Yes.
Okay. Excellent. And the second part of David's question is, what is the influence of all the sealings on the position resolved friction coefficients over the stroke, as you mentioned that you will have parasitic forces?
Yeah, for depending on the sealing. So when you have the belly, you are displacing it symmetrically. So this will not be seeable in some of the integral values. And normal sliding sealing, this will give a total offset of the signals. So we can get rid of that due to calibration processes. But to be on a very exact manner you need to calibrate it depending on your pressure you are applying, and also temperature. And yeah.
Okay, got it. Thank you very much. Are there any other questions from anyone in the audience? Please, we still have a. Oh, so that's great. Thanks for your question, David. Yeah, we have a few minutes remaining, so I just want to give anyone who would like to answer any question or ask any questions, excuse me, the chance to type them out now. As well, for anyone's information, if you have not yet, although it looks like there's been a good number of downloads of that, there are numerous handouts from Optimal Instruments in the handouts tab. Included in that is the informational handout on the hydrogen cell itself, as well as handouts on the SRV platform generally, and various other test configurations and test types that are able to be done, such as oscillating rolling element wear tests, high-speed lifetime false Bernelling tests, some information on the easy tribology screener, and tribological test design. So if you'd like any information on that, please go ahead and download those from the handouts tab. Although I believe they would, I assume, also be available from the Optimal Instruments website, Felix. Is that correct?
Yes.
Yes. So now is not your only chance for that.
Also, feel free to contact our sales person.
Yes. Of course. Okay. It doesn't seem like there's any other questions from anyone. So I think with that, we shall start to wrap up the event. So thank you very much, Felix, for your very comprehensive presentation and the answering of our questions from David. So I'd like to thank all of the speakers from today for their fantastic presentations, contributions, and answers to all the questions. Thanks also to all the audience members that have been here today. Thank you for attending live, for asking those questions. It's great that we can have these discussions and share information about the fields of tribology and material science. Thank you very much to Optimal Instruments for the support for this event. We wouldn't be able to do what we do without our partners. So it's fantastic to work with Optimal on this. As a reminder, please do visit our website, surfaceventures.org. You'll be able to see our next event, our next keynote, which will be on our website soon, but I can share the link for that now, so you can go ahead and register for that event. That will be on the 11th of September. So please do keep a lookout on our social media, LinkedIn, X, formerly Twitter, and email announcements for further updates on that event. Tomorrow will mark the last regular issue of our Modern Surface newsletter, so please do check that out on LinkedIn. After this, our content that was in our newsletter will be shifting to regular social media posts, so you'll still see some of the resources and recommendations from us on papers, academic resources, and the occasional lighthearted items. So please do check that out. And finally, I'd like to say to all of you, if you can, please do take the time to advertise what we do and promote what we do, please, and share what we do with your network of contacts. It would be great for us to continue growing and to continue sharing this information with many others. So if you can do that, that would be much appreciated. So right now, thank you all very much. See you next time. Thanks for joining today, and have a great rest of your day. Goodbye, everyone. Let me see from Marco. Thank you also that for the kind words on my hosting. But yes, have a great day, everyone. Bye.